Oh, good morning, everybody. Welcome to another exciting morning of chemistry, Chem 1211, with your host, me, Dr. White. Now, hopefully, none of you hear clicking. If you don't hear clicking, give me a thumbs up. Yay! All right, I better explain how I solved it. Well, for many years, let's see, can I grab one? I used the Saberin 4 connector USB hub. It's not powered. And I usually only have one thing connected. Well, when we went to video Zoom and all that, what did I do? Well, I hooked it up to a cable. By the way, behind me are my computers. So I have a special repeating cable. And I have my hubs here for my mouse, my two cameras, and my tablet. Well, Dr. White's hobby is electronics for a long, long time, and I should have known better. And it finally dawned on me Monday after class, how much power am I pulling? Because I know a USB port, the 2.0 can only take 500 milliamps, and the 3.0 is about 900 milliamps. And sort of like if you plug too many things into an outlet and you blow the circuit, well, my old camera could function on less power. My newer one needs a full one. So how did I solve that? I bought a self-powered USB hub that I got. Luckily, I have Amazon Prime. Ordered it Monday, got it late last night, put it in this morning, and no clicking. Better camera. All right, a couple important announcements from the management, me. Number one, this Thursday and Friday, we'll be doing lab number 2. It'll be the first one with Beyond Lab Z. You'll actually be doing. Relax. If you don't have Beyond Lab Z put in yet, you got a couple days, even on Thursday or Friday, whichever day you have the lab. If you don't have it up and running yet, you can still come and listen and see what I'll do with the lab. I have posted in Blackboard in the assignment area, lab number 2 for you to download. You can download it before, during, or after the lab. I'll go through it on Thursday for those of you in section 1 and Friday for those of you in section 2. And I'll show you how to use Beyond Lab Z for the density lab. All right, another thing, please upload the signature sheet. There are about 14 of you who haven't done that, and I need to know you're in, because I haven't figured out how to do attendance yet. Shh, don't tell anybody on here. So that way I can do the roster verification. You don't get dropped from the class, and also you don't lose your scholarship. So please upload it to the assignment area, and that's that. All right, remember on Thursday or Friday, depending which day you have lab, I'll go through chapter 2 problem set. I highly recommend you do them before I do some of them. And I think that's about it. Let's get started. Thumbs up, people. Do you all see chapter 3? Thank you. I wonder if this might work better because I was pulling too much power from one port. We'll find out. All right. For those who don't know, you'll find out repetition is good for your grade. And let's go through the 3 states of matter. Everybody, what's the first one? Solid. What's the second one? Come on, together. Liquid. What's the third one? You don't have to turn on your mic, but you can.
Yes.
And the last one?
Yes.
Yes.
Let's do that again. That was pretty pathetic. Everybody, you don't have to turn your mic, but just if we were in a classroom, I'd be telling the class, more feeling, louder. First one, solid. Second one, liquid. And the last one, gas.
Gas.
And you should know a solid has indefinite shape or definite shape, definite volume. Forget about the compressibility. Liquid has indefinite shape but definite volume, and a gas has indefinite shape and indefinite volume. And if you forgot, go back and look at the video for the when I discussed this. By the way, I'm up to date on my videos. Don't forget, if you need to or want to, check out my Chem 1211 YouTube channel. It's up and running. I talked about a pure substance, a mixture, element, compound, and example of an element, it would be gold, silver, platinum, palladium. Ooh, that reminds me of a story I'll tell in a little while. I talked about different type of chemical properties matter has, and one of them is physical properties, and that's the characteristic that is observed without changing the identity of the substance. And do I have time? Oh, I do. Quick story. I was teaching a long time ago, Chem 1211. One of the students, she came in and said, oh, look, it's everybody, look at my new engagement ring. And we congratulated on her. It was a beautiful ring. And about 3 weeks later, she came to me in private before class and said, can you help me out with something? I'll try. She says, look at the bottom of my brand new ring. It's getting all scratched up and nicked. What do I do? And I said, well, what's it made out of? I knew it wasn't gold. She said, platinum. I said, oh, platinum is a softer metal than gold. That's a physical property, and therefore there's nothing you can do about it. And I didn't want to tell her because she was already distressed because they paid a lot of money for that ring. I said, was thinking you should have bought gold, but I kept my mouth shut. Sometimes it's good to do that. And that's a physical property that unfortunately she didn't know about. Platinum is a softer metal than gold. I'm not sure about palladium. I don't know if anybody ever makes rings out of palladium. But anyways, let's move on. I talked about chemical properties such as gasoline will burn very quickly, water won't. And I talked about physical change, and this is generally when something changes its physical appearance but not its chemical composition. Oops, I forgot to do something. If I don't turn off proofing, you'll see all these little lines on your slides and my slides. There we go. An example of physical changes, ice melting to become a liquid, or water becoming a solid. Those are all physical changes. Example, another one would be water boiling. Oh, here's a good one. How many of you have ever seen dry ice? How many of you ever played with it? Dr. White hasn't. I've used it in the lab. And dry ice is called that because one, it's very cold, like ice. It's actually minus 78 degrees Celsius. And when it melts, quote unquote, because of its physical property, it undergoes a physical change from a solid directly to a gas. Now, if this were a 2-semester course, I'd be teaching you about phase diagrams, which I'm not in this one, and you'd learn why that does it, but it does it. And the other type of thing is a chemical change, and a chemical change is a process in which a substance undergoes a change when change in its chemical composition. And sometimes we'll call it chemical reactions, which I'll talk about later in a later chapter. Now, what would be an example of a chemical change? Guess what? When you eat food and it goes in your stomach, the food is undergoing a chemical change because the proteins, fats, or carbohydrates are broken down in smaller, different chemicals. And another example would be a chemical change is when you burn a candle, the wax is being burned and undergoes a chemical change and becomes carbon dioxide and water, plus heat. The heat you see as the flame or energy. And I talked about how, and we'll learn more about this, conservation of matter. Matter is never created or destroyed in a chemical reaction. I'll skip the energy part. Talked about temperature on Monday. We have degrees C, Celsius. Kelvin is the absolute scale, so there's no degree K, it's just Kelvin K. And finally, Fahrenheit, which you're probably most familiar with, degrees F. Quick public service announcement from Dr. White. If you haven't checked the weather report, starting tomorrow and this weekend, it's going to get cold. So make sure you got your warm stuff ready to go. And also another one, make sure you have your gas tank in your car filled. Do that today, because what happens is, well, it's not that bad because they now put ethanol in gas. You'll see that on the placard by the pumps. This gas contains 10% ethanol. That helps keep water out of the gas line from freezing up in this cold weather, but it's still good to have your gas tank full. At least I do. And I showed you the different formulas for converting. We have here Kelvin equals degrees C plus 273. Remember, 273 is the exact number. Next, Fahrenheit equals 1.8 times degrees C plus 32. And 1.8 and 32 are both exact numbers. Don't play a role in how many significant figures your final answer has. And finally, going from Fahrenheit to Celsius, degrees C equals degrees F minus 32 divided by 1.8. And 1.8 and 1 here and 32 are all exact numbers. Now, I showed you some examples. Next week, we'll go through the problem set for chapter 3, and I have a whole section of you doing temperature problems, and we'll go through it next week. Now, one of the things I mentioned, by the way, quick check, clicking gone? Success, it feels good. By the way, a life lesson, one, never assume, and also think about things before you do it. And for Dr. White, me, I never give up on a problem. Dr. White loves to win. He hates to lose even more. All right. One of the things I mentioned the other day, and I'll mention again, about a year and a half, almost 2 years ago, I came to the conclusion I'm teaching chemistry, and on a test, I'm trying to find out how you know the chemistry, understand it, and show me you can understand the chemistry that I taught you, not how good your memory is. And therefore, these formulas will be given to you in the packet for test number 1, and it'll be under what I call the last page or two, important information. You don't have to memorize them. I used to do that in the past. But you do know how to properly use those. And finally, a quick thing about heat capacity. All substances have what's known as a specific heat, and the heat can be calculated from the following calculation or formula. The heat of something, usually in joules, but it can be in calories, is mass times the specific heat times a change in temperature. And we'll be doing a lab on this later in the semester, and this will not be on the test ever or the final. Let me repeat that again. This will not be on the test or final. Click this slide. I've turned the switch. Will it be on test or final? Off. And guess what time it is? It's time for a new chapter. Wow, we're moving along nicely. That reminds me of a quick story. about a year and a half ago, year or so ago, it was it last year? No, 2 years ago. I had a Chem 1211 or 1105 class, about 24 students. It was a single section. And I do that. Guess what time it is? Everybody will close their notebooks, get ready to leave. I said, no, it's not time to leave yet. It's time for a new chapter. So let's go to our new chapter. And that new chapter is chapter 4. Everybody see chapter 4 on their screen? Thank you. Let me just do something real quick. Close some windows. All right. This chapter is about atoms and elements. And finally, we're going to get into some serious chemistry and have some fun. By the way, if I say fun enough times, you might believe me, but really, it should be fun. When we talk about chemistry, one of the most important aspects of chemistry is the atom. I think you've all heard of the Atom Ant cartoon. I may have just done a generation gap thing on you. But anyways, what's an atom? An atom is the smallest element, a particle of an element that retains all the characteristics of that element. And I'm going to be subtle today. Hint, know this. Again, atom is the smallest particle of an element that retains the characteristics of an element. So if you have an atom of gold that has all the characteristics of gold, if you have an atom of, I don't know, sodium, it has all the characteristics of sodium. And I'm never going to ask, but in case you were wondering, the word atom comes from the Greek word atmos. I probably pronounced it wrong, which means indivisible. I don't speak Greek, but I have had people who do, and they confirm some of the stuff I put in these slides. So, atom, the smallest particle of an element that retains all the characteristics of that element. Now, how did we come about this? Well, back about 1800, chemists or scientists, I don't know if they were called chemists yet, had all these weird theories about matter, substances in our life, gold, air, water. You forget, water is a chemical. And at that time in 1808, one of the greatest chemists, an English chemist, Dalton, came out with his atomic theory. And you should know this, at least parts of it. Well, first thing is every element is made up of small particles named atoms. And when you see these things, you probably go, duh, it ain't that. What's so special? Well, back then, people argued he was wrong. He wasn't. And this was quite special. And to this day, we follow it. Atoms of a given element are identical to one another. Atoms of different elements are different from each other. Atoms of two or more different elements combine to form compounds. And a particular compound is always made up of the same kind of atoms and the same number. So if I were on, say, in Glen Ellen, which we're not, but if we were at campus, the water that they have in that building, HSC, is H2O. If I go to, I don't know, where's a good city? Seattle, Washington. Water is H2O, 2 hydrogens, 1 oxygen. I'll teach you about the formula of this chapter. And if I were to go to the rings of Saturn were supposedly have ice, which is a form of water. Water there is H2O. So this was at that time, 1808, very profound statements that even some scientists refuted or tried to. And a chemical reaction involves the rearrangement, separation, or combination of atoms. Another way of putting it is when you have a chemical reaction, atoms are never created or destroyed during a chemical reaction. They're just shuffled differently, connected differently. So this is Dalton's theory, atomic theory, and he was the one who came up first with the, at least published, that what atoms are, that atoms are for a given element are identical and different for other elements, that atoms combine to form compounds, and they always have the same makeup, the kind and same number of atoms and the same number. By the way, I might have mentioned, I think I already mentioned this, but I'll do it again. If you look at the white solid that you put on your French fries or when you cook, sodium chloride, table salt, it's always got one sodium, one chlorine. And if you're out with lunch, breakfast, or dinner with Dr. White or other chemists, one of us will always, and I've done this too many times, could you please pass the knuckle? All right. Now, when we talk about atoms, they're different parts of an atom. And those particles or parts are called subatomic particles. And what's subatomic? How many of you are familiar with what a submarine is? Hopefully you all are. A submarine is a boat that goes under the water. Sub means under, marine, water. Oh, by the way, good news, I'm not going to start singing Yellow Submarine. I said I wouldn't sing it. But anyways, yes, I'm not a big Beatles fan. I like the Yardbirds better. If you don't know who the Yardbirds are, oh, I don't know if I put it on. If not, in the next week in Blackboard on the left, you'll see Dr. White's favorite songs and movies if I haven't posted it yet. And I don't know if I told you my claim to fame is in high school, I saw Jimi Hendrix live, probably the greatest concert I ever went to in my life. All right, so a subatomic particle are particles that are smaller than an atom. And these are very small particles that are building blocks from which atoms are made. All atoms of all elements are made from these subatomic particles, no exception. Can I get any bolder font? You should know these. Hint, the first subatomic particle is an electron. And electrons are subatomic particles that possess a negative charge, electrical charge, which we show like what I have in the bracket. You should know electrons, negative charge. The next one is a proton, and proton is another subatomic particle. And the protons possess a positive charge. Electron, negative charge, proton, positive. We show negative like this, positive like this. So electrons, negative charge, subatomic particle, protons, and the last one are neutrons. And neutrons have no charge. So the three subatomic particles that you should know electrons. And you should know electrons have a negative charge. Protons have a positive charge. They're another subatomic particle. And the third one, there are only three, are neutrons, and they have no charge. For those who are familiar with cartoons, have you ever seen Jimmy Neutron? If I were asked about that show, which I wasn't, I wouldn't call them. The neutrons are just hanging along for a ride. The exciting ones are the electrons. I would have called that show Jimmy Electron, but maybe it was just too dangerous to have kids thinking about electrons. That was awful. But anyways, I would call it different. It's time for everybody, class participation time. You don't have to turn on your mic, but let's go through the three subatomic particles. The first one, everybody, electrons.
Electrons.
Thank you. Second one, protons.
Protons.
And the third one, neutrons.
Neutrons.
And you should know an electron, negative charge, proton, positive charge, a neutron, no charge. And on a test, if I could ask you, what are the three subatomic particles? You should know electrons, protons, neutrons. If I ask on a test, what's the charge on an electron? It's negative. If I ask what's the charge on a proton, it's positive. If I ask what's the charge on a neutron, I usually don't because they're not that exciting, but it would be no charge. So the three subatomic particles, everyone, electrons, protons,
neutrons.
I did it fast on you. We'll do this again. So all atoms are made up of electrons, protons, and neutrons. It's time for Dr. White to scare the class. Everybody, look at your hand. Touch it. Hopefully it won't hurt. That's made up of atoms, and every atom that's made up, going to make up your skin, you can't see them unless you have X-ray vision. I don't, but I do know right here, there are electrons, protons, and neutrons in your skin. Also, what's left of Dr. White's hair and my top and everything else you see. The box back here, my wall, the paint that makes up this wall, everything. My metal file cabinet there, my printer up there, those are all made up of electrons, protons, and neutrons that make atoms, that make molecules, that make the stuff we use in our daily life. And which is why I always laugh when I hear someone say, I hate chemistry. Well, if you hate chemistry, you don't like being around. Because if it wasn't for chemistry, we wouldn't be here, because what would we be made up of? Nothing. And I'm not going to get into the religious part of that. I keep that out of the classroom. But everything is made up of atoms, and those atoms have the three subatomic particles, electrons, protons, neutrons. So next time you look at something, think about that. That's made up of atoms that are, have subatomic particles, electrons, protons, neutrons. Now you know Dr. White repeats things a lot. Now, when we look at the subatomic particles, how did we find out things like electron has a negative charge? Switches on Thomson's cathode ray tube. By the way, a cathode ray tube, for those of you who remember, and now I got to worry about doing a generation gap thing. How many of you remember the old television sets that were big and clunky with the glass and the big tube? Those are cathode ray tubes. And what's happening, how you got the picture screen, is electrons are being shot to a fluorescent front of the tube. Well, before television, back about 1900, give or take a couple of years plus or minus, Thomson, who was a great chemist, I believe American, but don't quote me on that, determined by his experiments that electrons have a negative charge. And the way he did it is he had a cathode ray tube, like your TV, old TV, an electron gun, which they invented. Then there were two plates that had a charge. He could put negative, positive, or other. And by doing it, he could deflect where the dot that came from the electron beam on the screen was. And the thing that deflected it was it always, the negative side deflected it. And that's how we learned, and you should know, Thomson's cathode ray determined electrons have a negative charge. I'll say that again, slow motion. You should know Thomson's cathode ray tube experiments determine that electrons have a negative charge. Now, give me a second because I was running late this morning, getting my camera working. Oh, by the way, no clicking? Solved. Dr. White's going to party hard tonight. No. All right, give me a second. All right, does everybody still see Thomson on the screen? Thank you. All right. Now, when we talk about a atom, where are the different parts? And we call something the nucleus, and that's the center of the atom. And this is the nucleus. It's the center of the atom. And then there's something not in the nucleus. So the question is, how do we, we have these subatomic particles, electron, proton, neutron. Well, how do they fit together to make an atom? And that's quite an important thing to know. And person who really helped that, determine that, I'm going to use a fancy word for you, elucidate. Elucidate means figured out, solve, but it sounds fancier. You know you're going to learn 50-cent words in my class, and dollar words that you can impress your friends, neighbors, and loved ones with. All right, Rutherford elucidated what was in the nucleus of an atom. How did he do that? By gold foil experiments. And just in case, aren't you glad Dr. White knows you can't read my mind? I couldn't when I was a student read my teacher's mind. But anyways, Rutherford's gold foil experiments, what did he determine? That the nucleus is very dense, very heavy, high density. And we'll learn about density on Thursday and Friday. And the nucleus, which is very dense, contains only protons and neutrons. You should know this. And the electrons are outside around the nucleus. So here, if I have a nucleus, I have my protons and my neutrons, and all around I have my electrons. Because you know The three subatomic particles are electrons, protons, and neutrons. And in the nucleus, and you should know the nucleus is the center of the atom. That it has protons and neutrons. Now, how did he do this? Well, let's take a look. Let's try something. Yes, it worked. It doesn't always work. Does everybody see Rutherford's gold foil experiment on your screen? Thank you. All right. Now, what Rutherford did, and I'll explain really he didn't, I'll explain why I'm saying that, but his experiment was he had a very high energy radioactive source that sent out very high energy particles, very fast, very high energy. And it had very thin gold foil. How many of you have ever seen gold foil, gold leaf foil? And it's very, very thin, like the skin of an onion. And around it, he had a detector. And this was a screen that if any of these, wherever these particles ended up, it would be a glowing dot. Beyond Lab Z has an experiment to do this. Feel free to play with that if you want. I didn't include it in the semesters, but it does work. You can do his gold foil experiment. And think of this as like shooting a cannonball at a piece of tissue paper or Kleenex. I'm using a product that you're all probably familiar with. Well, if you shoot a cannonball at a Kleenex, what do you expect? It to go right through. Well, some of them did, but they got deflected. If you notice this one, it actually bounced back. And that was amazing. It shouldn't have done that. It should have been like shooting a cannonball through tissue paper, go right through. Now, let me explain something about what really happened. At least I think so. If you're a graduate student getting your PhD, like I was long ago, in chemistry, I don't know about the other disciplines, but I know about chemistry, you are essentially like a plumber's apprentice to someone who knows chemistry. In the case your plumber's apprentice would experience plumber, learning about it. My case, my PhD advisor, and I was in his research group, was Dr. Roosh, who I will forever be grateful for what he helped me learn and the foundation I have and built on for organic chemistry. And the way it works is you join a group, you tell a professor, I'd like to be in your group. The reason I picked that, because he was doing research in areas that I was interested in. And they decide, well, yeah, I want you or I don't want you. I've heard people, no, we don't really want you. But anyways, he said, sure. And I joined his group. We had about 12 PhD candidates in the group. It was a good sized group. And you would work on a research project he assigned you. And when we had group meetings where you'd talk about it. And if you're having problems or something unexpected come up, you go and talk to them about it privately. And generally, if you have something really unexpected happen, you'd say, and I'm sure other professors in Rutherford did the same, go back and do it again. And if you got the same results and it was really unexpected, do it a third time. And if you got it again, he'd come out and watch you do it. Well, I can see Rutherford's a graduate student doing that. And I think one of them, and I think it was Rutherford, was a graduate student. You might be familiar with the name Geiger. And Geiger developed the Geiger counter because they were working with radiation. But anyways, I can see Rutherford telling the grad student, it bounced back? No, you did something wrong. Do it again. And the grad student did it again, come back and said, it bounced back. The particles from the high radiation when it hit the gold foil came back. what? And Rutherford would say, do it again, third time. And the graduate student came back third time. And he probably the fourth time went out there and it did happen. And then he was smart enough to elucidate what that meant. First of all, it was very dense. Only something very dense would be like a steel plate to bounce back to cannonball, in this case, radiation. And that's how things are found. One of the things I just glossed over the first day is how do we come up with theories, hypotheses, and how do they become facts or laws in science, especially chemistry? You go into the lab and do experiments. And everything I'm teaching you this semester, or anything with chemistry that I know of, has been proven true by going into the lab and doing experiments and observing. All right, so you got to learn all about how you get your PhD. It was one of the fun times of my life, even though sometimes it was very stressful when you couldn't get things to work, which is a major part of chemistry, organic chemistry. But anyways, again, you should know Rutherford's gold foil experiment. What part of the atom did it elucidate, clarify? Ooh, I'm using big words today. And that is the nucleus. And you should know the nucleus is the center of the atom. And what's in the nucleus? Protons and neutrons. You should know that. I do, now you do, and you should know that. And where are the electrons? They're outside of around the nucleus. So when we have an atom, and this is true for every atom of every element, those all have a nucleus with protons and neutrons. Remember, proton plus charge, neutron no charge, and around are the electrons. Now, there's an important thing called the atomic number, or also known as the mass number. I always call it the atomic number. Hang in there. All right, where did I? All right, I've hidden it from Dr. White. Hang in there. When in doubt. Actually, it's a good thing I couldn't find it. If you go to course information, go to lectures, and you'll see periodic table. If I click on that, we got a periodic table, which I'm going to download. Well, I can't find it in mine. Does everybody see the green thing on your screen? Now, when you open up the PDF, you look at that and says, oh no, I'm going to hurt my neck. No, watch closely. If you do Control Shift positive, oh, okay, Shift pos. Why are you not rotating? Oh, I know why. I'm using the wrong one. Let's do this. Oh, the joys of having. Well, sometime today I'll get to this. Hang in there. I apologize for not having one. All right. What happened was the periodic table, when I downloaded it, it downloaded, but I was still on my browser view of that. Does everybody see a small little one on the screen now? That is made larger. Thank you. Now watch. Control Shift plus. Now it works. Now, this is a periodic table. This is a periodic table you will be given for every test in a final. And notice it has the different elements. Hopefully you've learned by now the 37, H is hydrogen, Li lithium, C, my favorite one, carbon, and nitrogen, O, oxygen. Now, if you look in the upper right-hand corner of this periodic table for each little box, which is one of the elements, like oxygen here, you'll see the number 8. That is an atomic number. If you look at carbon, it's 6. You do not have to memorize the atomic numbers. I do, because a lot of them I use often. Oh, by the way, over here is krypton, and our universe, unless I've been stolen to another universe, is a colorless gas, not a green solid that will kill Superman. And above it is argon, Ar, and the atomic number for argon is 18. Neon, 10. How many of you have ever seen neon signs? And they've used neon gas in those. Helium, atomic number 2. How many of you ever had the party balloons that float real well? Because they put helium in there. And that has an atomic number of 2. And if we go over to, how many of you heard you have to have calcium for strong bones? And calcium, Ca, has atomic number of 20. So here's the periodic table. It's the first thing in Blackboard in the lecture folder under course information. And for each test, I will give you this one. It will be in the assignment area for you to download. Now, why is Dr. White making a big thing about the atomic number? Because the atomic number, everybody see atomic number and mass number? Atomic number tells you the number of protons in the nucleus. This is one of the more important things I'll teach you. Oops. When I took notes, IMP meant important. You better know that. Atomic number, that's the number of protons in a nucleus. Now, I haven't taught you this, but I will. If you can't read my handwriting, I'll decode it for you. All atoms have a net zero charge. If you have an atom of gold, what's the charge on there? 0. If you have an atom of carbon, 0. Therefore, if protons are positive charge, in order to have a net zero charge, the atomic number, which is by definition the number of protons, also tells you the number of electrons. So all atoms have a net zero charge. And because of that, the atomic number tells you the number of protons and the number of electrons in an atom of an element. If I look at the clock, it's time for a break. And Doctor wants to get up and do his stretching exercises. So I'll see you at 5 minutes, 10:55. Enjoy your break. And welcome back, everybody. It's time for more exciting chemistry with your host, Dr. Whitey. Now, just to remind you, what are the three subatomic particles? They are electron, proton, neutron. Remember, electron has a negative charge, proton positive charge, and neutron no charge. And my camera's still working good, no clicking, right? Another one solved. Actually, it's a problem I caused myself. But, anyways, let's get back to where we were talking about. Everybody see atomic number? I think that also probably could have affected my overall computer, so I'm having less problems with Zoom. I better keep my mouth shut. All right, now the atomic number tells you the number of protons and number of electrons in a atom of an element. And remember, all atoms have a net zero charge. All atoms have a net zero charge. So let's look at the following. Oh, come on. And hopefully, let me check because I opened my mouth, said no problem. Everybody see 2 points each on the screen? Thank you. And if sometime in the future you see on something I send out to you called the test, 2 points each. How many electrons and protons are in? I'll type this, I won't handwrite. Sodium. This is a sneaky question because I'm asking a few things. One, you know what the chemical symbol of sodium is. See how sneaky Dr. White is? And two, you know what the atomic number means. So let's take a look at this one. If we have the periodic table, which you will, and notice this one has no names on it. I don't know if you're cheating if you're using one from the internet. Please don't, because I'll do what's in my syllabus. Trust me, I will. Sodium, chemical symbol or atomic chemical symbol. Na, you should learn those. How many electrons and protons? Look at the atomic number, and it is 11. By the way, I haven't figured out yet how to use my pen tablet on a Word PDF document, so that's why you're just seeing the cursor. So atomic number sodium is 11. Therefore, I can do this. Sodium has 11 electrons and 11 protons. I'll abbreviate. Nope. Someone asked, do I mean protons and neutrons? No. I'll talk later how you can figure out how many neutrons. And really, I can't remember what decade I did that last personally. It's not important. The important part of the atom, the key ones are the electrons and protons. And of those, the most important are the electrons. Dr. White loves electrons. I've been nice to them. They've been nice to me. All right. So again, we're asked how many electrons and protons are in sodium. The answer is yes. For an atom of an element, the number of protons and electrons are always the same. Oh, I should say, if anybody finds an exception to this, let me know, and we'll be rich beyond my wildest dreams. That goes beyond me having my own fleet of jets, my own island in the South Pacific, and my own Lamborghini and Countach. If you don't know what those cars are, look them up. I've been in a Countach, actually a Lamborghini is, a Countach is, I should have said Lamborghini or Ferrari. I've been in both, but I don't own them yet. But it won't happen. Always the electrons and protons are the same in an atom because all atoms have a net zero charge. Oh, let's do another one. These are fun. Oh, let's go to the high rent district. How many electrons and protons are in silver? If we come over to our periodic table, which hopefully you see, silver, all you have to know is silver has a chemical symbol Ag, and it's right here above gold. And how many, what's the atomic number of silver? You look in the upper right of this periodic table, and it's 47. And therefore, I know the atomic number tells me the number of protons and the number of electrons, in this case 47. So I can write down 47 electrons and 47 protons. Oh, by the way, this weekend at a Super Bowl party, don't teach people about electrons, protons, and neutrons. They don't like hearing chemistry at Super Bowl parties. Hopefully you're going to virtual ones, not unless it's your immediate family. All right, I'm going to share the fun. And let's go back, and it's your turn to find out how many electrons and protons does oxygen have. And here's your periodic table, go. I'll give you 8.65 seconds more. 8, 8.2, 8.3, 8.4, 8.6. I got a slow stopwatch. Time's up. Oxygen, what's the chemical symbol? O. Therefore, here it is on the periodic table. How do you determine how many electrons and protons? You look in the upper right-hand corner and you say, oh, it's got atomic number of 8. It has 8 electrons, 8 protons. Oh, let's do another one, but first let me check chat because I think some of you are helping me out. And the answer everybody got right. Doesn't that feel good? You're learning chemistry and it's not that hard. It shouldn't be. All right. How many electrons, how many protons does bromine have? And let me get you back to the periodic table. Your turn. See how sneaky I am? You got to know the chemical symbols. And I'll only do the 37. All right, I'll give you another 4.76 seconds. 4.1, 4.3, 4.7, 4.7. Time's up. And bromine, what's the chemical symbol? Br. It's right here. And the atomic number tells you how many electrons and protons. In this case, 35. And therefore is the atomic number. That means it has 35 electrons and 35 protons. And if we look over here, krypton has 36 electrons and protons. And while we're over, oh, let's pick a good one. Copper. Copper is what makes up the wire in all the devices you use, like your power cords and stuff that carry electricity. And copper atom has 29 electrons, 29 protons, because its atomic number is 29, which we look in the upper right-hand corner of the periodic table. Oh, let's do one more. Magnesium. Magnesium has how many electrons and protons? It's 12. 12 electrons, 12 protons. How would you know that, Dr. White? Well, I looked at the atomic number, and it's in the upper right-hand corner of the periodic table. By the way, how many of you are familiar with chlorophyll? That's the stuff in plants that make it green and convert sunlight to energy. In the center of the molecule chlorophyll, there's magnesium. And if there was no magnesium, guess what? No chlorophyll. We'd be dead. Speaking about being dead, how many of you are familiar with hemoglobin? It's stuff in your blood that carries oxygen to the cells. Now I'm going well beyond my knowledge of biology. I don't know if I told you this, last time I took biology was freshman year of high school. Not that there's anything wrong with biology, but even by then I knew I wanted to be a chemist, so I didn't take any more biology. I took a lot of chemistry. But in hemoglobin is similar structure to chlorophyll, made a mistake there, chlorophyll, except instead of having magnesium in the center, it has iron. And that allows your blood to transport things like oxygen in and carbon dioxide and other gas waste out. Ooh. From the, how should I say this? From the area of totally useless or not useless, but unimportant information. Do you know when you burp, most of the gas when you burp is carbon dioxide? All right, let's get back to chapter 4. So remember, atomic number, number of protons, number of electrons, because, oh, I didn't put it down here. I better. Protons have a plus charge, electrons have a negative charge. If all atoms are to have a net zero charge, which they do, the number of protons, which is the definition of atomic number, also equals the number of electrons. No exceptions, period. Oh, it's time for a commercial from Dr. White. But first, I think I have a question coming up. Oh, why am I missing 110 through 118? Because this is an older periodic table that I scanned long ago before those were discovered. And by the way, you can ignore those because in my lifetime, I will bet I will never use those, and either will you. I think I already mentioned if I say I bet, I already know I won. And that's why. I'll talk more about the periodic table later on, but the top part is the most important part. All right, back to a commercial from Dr. White. Chemical symbols, one or two abbreviation. I'll never ask on a test, what is a chemical symbol? Never. But when you write them, you should know that the first letter is always capitalized. If there's a second one, it's lowercase. So if I have carbon, oxygen, nitrogen, I have sodium, Na, magnesium. Notice how second letter is always lowercase. It's not Mg. That's a car. They're fun cars. I had a friend who had an MG. When you're driving in one, you're about real close to the road, very low ridings. Anyways, and those, bromine is another example, and even chlorine. So you should know that the first letter is capitalized, second letter lowercase. And you need to know these elements and their symbols. If I ask you, what's the name of the chemical element with this chemical symbol Li, it's lithium. If I ask, what's the name of the element with Fe, it's iron. If I ask, give the chemical symbol for argon, and the chemical symbol for argon is Ar. If I ask, give the symbol for uranium, U. If I ask silver, Ag, what's the name of the element, Au, gold. You should know those. How do you memorize those? Well, you could try flashcards. I never liked flashcards when I was a student, and a lot of my students, I taught a better way that worked better for them. But if you like flashcards and they work for you, go for it. And you should know these. And that's my commercial for chemical symbols. Now, what I just showed you is called the periodic table. And I'll never ask you what's the periodic law or what's the periodic table. Well, let's go through. Turns out, and I think it was Mendeleev was the one who came up with the final periodic table. A number of people were working on it. When elements are arranged in order, excuse me, of atomic number, increasing atomic number, elements with similar properties occur at periodic regular occurring intervals. So because of setting up the elements based on atomic number, we were able, chemists, to come up with called the periodic table. It's a table, tabular arrangement of elements in order of increasing atomic number, which elements of similar properties are positioned in the same columns of the display or periodic table. Now, we have what's called groups, and I'll never ask you what is a group, and also sometimes called families. Those are the vertical columns, up and down. The periods, which are somewhat useful but not as useful as the groups, are horizontal across the rows. Now, if I go to my periodic table, let me move this out of the way. Question is, how come these rows are down here? Because they actually go in right here, but these have different properties and they aren't used that much. So they're down here to different elements. And other than Lawrencium, because I know its name, and uranium, some of these are, but most of these are the key ones. And this helps fit this type of tabular arrangement to make these different families or columns work. Now, if you look over here, the first column, when we talk about families or groups, has hydrogen, and actually that's not included in the family of the other elements in this column. Now, each column or family has important names or has names. Now, key groups in the periodic table have special names, and those are the alkali metals, alkaline earth metals, the halogens, and noble gases. And we go back to our periodic table. The first column with the number 1 over, and I'll teach you what those red numbers are later on this semester. These are called the alkali metals. You should know that. The first column is the alkali metals. The second column, and the only one I've asked you to learn from the first column, are lithium, sodium, potassium, Lina and K. The second column are the alkaline earth metals, and that's magnesium and calcium. The other ones are too, strontium I like, and you'll see in a lab, we'll use that later on this semester. But The only ones I asked you to learn of the alkaline earth metals are calcium and magnesium. Now, if we come all the way over to second to last column on the right, fluorine, chlorine, bromine, iodine, those are the ones I asked you to learn. These are called the halogens. This, where number 7 is above the column, fluorine, chlorine, bromine, and iodine, those are the halogens, and you should know the halogens. By the way, how many of you have heard of halogen lamps? Guess what? They contain these gases in there from the halogens. Now, I'll teach you later on, the halogens exist in our daily life as diatomic molecules like oxygen, chlorine, and Cl2, but those gases make up your halogen lamps. If you've ever been in Chicago, you know how they have the yellow street lamps? You can see it from a distance. Those are halogen lamps, and they're very bright. Now, a lot of them are being replaced with others, especially LEDs, and those are the halogens. And the last column is called the noble gases: helium, neon, argon, krypton, xenon, radon. And I see someone with a question.
Do you just want us to know 1, 2, 7, and 8, or all 8 of them?
That's correct. That's all you're going to have to know. Thank you for asking your question. Now you helped out not only yourself, but a lot of students. And that's why I say there's no such thing as a good question. And I would bet, you know, if I say I bet, I know I won. If you had that question, a number of your other colleagues had it too. Now, the last column is called the noble gases, where number 8 is above. And I will, unfortunately, use the old name. Till about the late 1980s, early 1990s, this was called the inert gases. Then 1 or 2, I can't remember how many, very ingenious chemists found a way to make the noble inert gases react. They beat on it real heavy. When we say beat on it in chemistry, use a lot of force and energy that you normally wouldn't have to. Well, they did. And what everybody believed until about 1990s, that the noble gases, now called, were inert. That meant they can't react. These chemists showed, well, look, we made them react. So they had to change the name, and they're now called the noble gases, I think in honor of Alfred Nobel, but don't question me. And therefore, I will sometimes call them the inert gases, because back here in my brain it still pops up what that is, the old name. So bear with me. Let's see. All right. So you should know what's an alkali metal. If I ask on a test, give an example of an alkali metal, you should know that could be this. I'll go through that, Kelly. The second column, and I'm going to go through them all, are the alkaline earth metals. Ooh, I know what I can do. In a classroom, I'd put this on the board. This is column 1, 2, 7, 8. Does that help? Thank you. And as you see, Dr. White actually practices. There's no such thing as a dumb question in my universe, and I actually answer questions. All right, let me show you something really neat. Now you're going to find out Dr. White really is a chemist. You go to your favorite search engine, and let me just check something. Yep. Everybody see Google on their screen? Back when Google, about a week after Google actually started, I forgot, sometime in the 1990s, I was at a company and I was one of the few people who had internet connection. Back then, companies didn't want people to have it. It was expensive. They're afraid workers wouldn't do their job. They'd play on the internet. I just got it, and a friend of mine in California called me up at work and said, "You got internet at work?" And I said, "Yeah, I just got it." Go to your browser. You know what a browser is? I said, "Yeah, I have one." And type in this, www.google. I said, "What's a goggle?" "No, it's Google." He corrected me. And I looked at this, all right. And back then it was just the name and this box, nothing else. I said, "All right, what's exciting about this?" It says, "Type in a question." I did. And I said, "Oh, wow, that is exciting." All right, history lesson from Dr. White. Now, if you put in periodic table, and notice I didn't even have to put everything in, the first one that comes in is my favorite periodic table on the internet. And everybody see it on there? And if you look here, if I have over here alkali metals, it shows me which ones are the alkali metal. Is that cool or not? If I do alkaline earth metals, now they don't have the halogens, but they do have the noble gases. And they have a whole lot of other names, but I'm not going to ask you to learn those. But the noble gases you can see here. And if you notice the person who asked the question, these are put down here. They're part of that row, but it helps if you have the periodic table divided this way, or I should say formatted this way, to help chemists learn, see what's lined up. And this also allows you to get it on a smaller piece of paper. But that's why. But anyways, first column, alkaline earth, alkali metals. Second one, alkaline earth metals. Over here, they don't have it, but right here, fluorine, chlorine, bromine, and iodine, they have the halogens. And finally, the noble gases. Now, one of the nice things about this is you put your cursor in the box, you can see magnified in the upper left over here what element. And notice here they have the atomic number in the left, but the atomic number is always a large number, upper right or left. And I'll teach you more about the number here. Here you don't see this on a periodic table, normal one, but I'll teach you about what that means too. So you should know, first column, not hydrogen, and I'll explain that later in the semester why, but lithium, sodium, potassium, and the others too, but the ones I asked you to learn, the chemical symbol, are the alkali metals. Ooh, a lot of chemistry has gotten into our daily life. How many of you have heard of alkaline batteries? And that's because certain things in there. How many of you heard of the lithium power cells or batteries? Because they have lithium in them and they're dangerous because if they rupture, they will catch fire. Lithium, sodium, and potassium are very dangerous. Wait, ooh. Maybe in lab this Thursday and Friday, I just thought of something. I'm going to have a special surprise for you. Don't forget, Thursday and Fridays are labs. Speaking about special surprises, I'll put it out in an email, but I just remembered it's about time I do this. Years ago, I came up with a method based on somebody else's method to help eliminate test anxiety. If you get nervous during a test, and students get this, all of a sudden you know the material, but now I'm taking a test, you go, and your brain goes, and you get nervous and you don't get a good score. I have come up with an easy way that eliminates that. Next Monday, the first couple minutes of class, I will teach that. It takes about 10 minutes. I will cut that out of the video because someday I may try and sell it again when I get money to do it. I haven't yet, but I'll still teach it to you free of charge. Actually, you have to pay to register for this class. So it's not additional charge. But if you suffer from test anxiety, this will help. It's helped students who've gotten C's, D's, and F become A and B students, mainly A students. It's amazing. All right. Now, we've done some, but let's do a few more. Let's practice using the periodic table and determine a couple of things. Let's go back to our periodic table. Let me do a thumbs up, people. Everybody see the periodic table? Thank you. I think that power problem was affecting Zoom too. Hopefully it was. All right, everybody, determine how many electrons, how many protons does lithium have, and what family is it in. And I'll tell you afterward. You don't have to put it in chat unless you want to. If you enjoy doing that, I'm not going to stop you. Time's up. Lithium, Li. It has atomic number of 3. Therefore, it has 3 electrons, 3 protons. It's in the first column. It's an alkali metal. All right. How many electrons, how many protons, and what family is iodine in? Go for it. All right, time's up. Everybody turn in your pencils and your test. Oh, I can't do that. Anyways, iodine, atomic symbol I. It's a halogen, this column. And how many electrons and protons? The atomic number is 53. Therefore, it has 53 electrons, 53 protons. Let's do helium. What family is helium in? How many electrons? How many protons? What's the atomic number? All right, let's do helium. And if we have helium, the chemical symbol is He. How many electrons? Well, atomic number is 2. It only has 2 electrons and 2 protons, but those are enough. And finally, let's do one more, and that is, what's the chemical symbol? How many electrons and protons? What's the atomic number of hydrogen?
Sorry, Dr. White.
Yes.
For helium, do you prefer us to indicate noble gases or inner gases, or either one or the other?
It's now called noble gases.
Okay.
I just did a, how should I say, admission of guilt that my brain still sometimes pops up the old name. It's no longer called inert gases because somebody proved they aren't inert.
Thank you.
Which they did an amazing thing, but they've caused a lot of grief for me because how once in a while during this class we'll say inert, and if I do, everybody say, no, it's noble gases. All right, hydrogen, chemical symbol H, it's right here. It's not an alkali metal. And it's got atomic number 1, which means it's got one electron, 1 proton. And that's how you use the periodic table. And you only have to know 37 of these. And those are the ones that we use in our daily life. most of us, and like all of us. And that's why I limited to that. All right, here's some things, terminology. I think I have a question. Uh, Hydrogen really is not in a family of its own. Poor little hydrogen. Why that happened, I don't know, but that's just the way it is. You know, uh, and that's some things like that in chemistry. I guess if you got nothing better to do and you have free time on your hand, go to your favorite search engine and ask why hydrogen's not in a group. I'm not going to do it now. Maybe if I have a chance this weekend, if I remember. But that's how you find things out. All right. Now, certain things we use in our daily life terms come from the elements. First one is a metal. And you should know a metal has the characteristics, properties of luster, thermal conductivity, electrical conductivity, and malleability. What is luster? So I told you, you'd be learning a lot of new words in my class. And luster is the property where you can take a metal. Do I have something metal handy? Oops, here, this is metal. I'm going to show my age. I got this at a conference. This is an ancient Microsoft mouse that's a little LED flashlight. This is ancient, but I like it. And a metal is something you can rub or polish, and it's shiny. If you had a piece of gold, piece of platinum, or anything, it gets shiny like this. Now, a non-metal, you can rub all you want, and it won't get shiny. And that's luster. Now, what's malleability? Well, malleability of a metal is you can pound on it, and notice my pounding face, and you can make it thinner. And how many of you have ever seen gold foil leaf? That's stuff super thin. And how many of you are familiar with aluminum foil? I think most of you are. Let me take a look at everybody. Hi, everybody. Okay, you see, if you don't want to keep your cameras on, you don't have to. For those of you who do, thank you. I get to see all your pretty faces. You get to see my face. But anyways, aluminum foil, how is it made? They have big, thick ingots of aluminum, and they put them through mills, these wheels that they put pressure on. And because aluminum is a metal, it's malleable, it will thin out. And it gets thinner and thinner and thinner. Now, Dr. White likes the thicker aluminum, not the thinner ones. I don't know if I told you, if you're a good organic chemist, you're a good cook. I'm both. But anyways, have you ever noticed aluminum foil is shiny on one side and dull on the other? Have you seen that? Why is that so? Well, it's time to learn one of those mysteries of life. When they go to polish it, because aluminum is a metal and has luster, I'm throwing in two things you learned this morning. The metal going through the brushes to polish it, polishing wheels, is too thin and would rip. So what they do is they two pieces of aluminum foil together when it gets polished. Well, only this side and this side of each piece gets polished, and the other sides that are together don't. And that's why aluminum foil is shiny on one side because of the luster and not on the other. Now, if we go back, thermal conductivity means it conducts heat. And therefore, if you go in your kitchen, I think just about everybody there has metal pots and pans and oven roasters and everything, because that conducts the heat from the flame. Or if you have electric, I don't like electric, I like gas better. Ovens are also ranges. You have better control, at least I do. And that's why. Now, what's electroconductivity? Electrical conductivity, it conducts electricity. And wires in your house are from copper, which is a metal. Now, back in about the 40s or 50s, I was told they also used to use aluminum. But aluminum had a problem of overheating and causing house fires. And about early 1950s, give or take a couple of years, the United States, and I think everywhere in the world, but the United States, outlawed aluminum for any electrical wires. And here's some others: lead, tin, zinc, gold. I could also put down silver. Now, a nonmetal is something that doesn't have these properties of luster, thermal conductivity, electrical conductivity, or malleability. So what would be an example? Well, if you had carbon, like a lump of coal, no matter how hard you rub that, at least in a carbon form, it will never shine. It's not malleable. So if you have a diamond, and do not try this at home, if you hit it or push on it, bang on it, it will crack. It won't get thinner. Don't try that at home. If you've ever seen diamond cutters who make the rings and the different facets from the raw diamonds, use that property that it's not malleable. And also different things won't conduct electricity. Now, I'm going to turn the switch off. Other things are called metalloids. They have some of the properties of metal and some of the properties of non-metal. An example would be silicone, like in our semiconductors, in our chips, and our electronic devices, and that's important. All right, now, I'll be using this term and I'll never ask you what it is, but an ion is an atom with more or less electrons than protons. And it turns out this is pretty important. We'll spend more time on this. So when we talk about ions, we're talking about an atom that has more or less electrons than protons, because it turns out atoms of elements can lose or gain electrons, and they become something different, and we call those ions. So the actual atoms of an element always have a net zero charge, but ions do have a charge. And again, I'll never ask you on a test what's an ion, but I'll use that term a lot. Now, there are two types of ions, and this you should know. One is a cation, and the other is an anion. So two types of ions. That's where you have an atom that's lost or gained electrons. One is a cation, the other is an anion. How many of you ever heard of a battery to cathode and anode? That comes from cation and anion. Ooh, really? Yes. Chemistry's everywhere. Now, what's a cation? You should know a cation is a positively charged ion. It's got a plus charge to it. That's what we mean by positively charged. It has less electrons than protons. I've never asked that, but you should know what's the charge on a cation. And what's the cathode side of a battery? The plus side. And that's why I got the name from cation. Everybody got this down? Oh, remember, Dr. White has the fastest mouse wheel finger this side or the other side of the Mississippi River. If you've never seen the Mississippi River, it's awesome. And the other one is an anion. And an anion is a negatively charged atom. It has a negative charge. And that's because it has more electrons than protons. Remember, every electron negative charge, every proton positive. And you should know an anion is negatively charged atom. I'll say that again. You should know an anion is a negatively charged atom. So we have cations, positive charge, anion, negative charge. How many of you have heard the anode of a battery? That's the negative side of a battery. And if I look at the clock, oh no, time flies when you're having fun with Dr. White in chemistry. We are out of time. Quick thing. Those of you who have lab tomorrow, I'll see you tomorrow. Those who have lab on Friday, I'll see you on Friday. Don't forget tonight, I have my office hours. I'll go through that in a second, Marissa, but in case those of you want to leave on time can. I'm going over. Bad, Dr. White. We'll see you on Friday. Remember, if you haven't uploaded your signature sheet yet, do that by tomorrow morning. Please help me out. And with that, I'm going to say goodbye, and then I'll stick around for a couple minutes for questions. But gang gazoon, goodbye. This is from Granny from the Beverly Hillbillies. Bye. I'll see you either tomorrow or Friday, depending when you have lab. And don't forget, do the practice problems, chapter 2. And have a great day. Remember, it's going to get cold. Stay warm. And gang gazoon. Goodbye.